Hi everyone. So in this video, we're going to go over understanding solutions, determining if IV saline is isotonic, and we're going to use a calibration curve very similar to in a previous experiment. So that's kind of that. But before we do that, I want to talk a little bit about what osmotic pressure is, and you may have seen this before, so this may be a reminder, but I just do want to talk about a little bit about what that is, not in great detail. So basically, in osmosis, water will flow from an area of low solute concentration to an area of high solute concentration. Said another way, nature tends to dilute solutions. So if we look here in this U-shaped tube, what we have is on one side pure water and on the other side salt water in our case. Now, this could be different solvents and solutes. In this case, our solvent is water and our solute is salt, but basically it works in a similar way. So what happens here is that the water through this semi-permeable membrane is able to pass, but the salt ions are not able to pass through this semi-permeable membrane. So water can move and salt can't. And what you're going to find is the rate at which water flows in this direction is greater than the rate at which it flows towards the pure solvent. Said another way, it flows towards the solution more than it flows towards the pure solvent. And if we come back sometimes later, what you'll see is there's actually more liquid in the solution side because some of the water has flowed towards this, and you end up with this difference in height, which could be understood as an osmotic pressure. That's not super important for here. What's super important for here is to know that nature tends to dilute solutions and that pure water will flow towards salt water and not the other way around. So that's basically how it works. If you want to think about this kind of from a molecular level, the salt ions act like little magnets and they attract the water molecules. So that's effectively a simplified way of thinking of what's going on. So the salt molecules, the water molecules want to be near the salt molecules, so they move towards it, and you end up with a greater volume of solution than you end up with of pure water. Now, if we think about this in terms of cells, we can think of this in terms of the cell wall as being the semi-permeable membrane. So the cell wall is a semi-permeable membrane, and it turns out that the osmotic pressure of our like blood is 0.9% NaCl. Now you don't have to use NaCl as the solvent, or excuse me, as a solute. You can use other things like glucose, for example. But in this case, we're going to use NaCl as the solute. So what we're looking at here is an isotonic case. So if we have 0.9% NaCl, water will flow into and out of the cells at the same rate because the osmotic pressure inside of the cell, or the concentration of solute inside of the cell, is 0.9%, and the concentration of salt water outside the cell is also 0.9%, so water flows in and out evenly. If we put it in what's called a hypotonic solution, which is less than 0.9%, including pure water, the water flows in. Why? Because it's 0.9% NaCl inside the cell and 0% NaCl, if it's pure water, outside the cell. So water flows into the cell. Well, what can happen? The cells can actually blow up like a balloon, and they may actually burst, and this is called hemolysis if they actually burst. And this is a common way to destroy cells if you're looking to get something from inside of the cell, for example, if you're doing biochemistry type of research. We can also have what are called hypertonic solutions, where the concentration is greater than 0.9%. So now it's 0.9% inside the cell and greater than 0.9% outside of the cell. So this is, for example, like seawater, for example, would be about 3.5% NaCl. So this would be a hypertonic solution. In this case, the water flows out of the cell because it flows into the higher concentration outside of the cell, and this can cause the cells to shrivel up and potentially die. So this is basically just a little introduction to osmotic pressure and osmosis, and it's not super important here, but it is what we're trying to do. We're trying to figure out if the unknown solution is basically safe to be used inside of a person. Obviously, it's not actually safe because it's not sterile or anything like that, but we're trying to determine whether or not, if we work for a company who makes saline solutions that go in IVs for to put into people, well, does it have the right concentration? Because as you can see from this, it's very important that it has the right concentration. So the next thing we want to talk about is a calibration curve, and you've done this before. So what a calibration curve allows us to do is it allows us to replace something that's easily measurable, in this case conductivity, which we're going to measure with a conductivity probe, and we'll show you that in a little while, and versus the salt water concentration in percent by mass. Okay, so we're going to make a 1.2, a 1.1, a 1, a 0.9, and a 0.8% saltwater solution, and then we're going to use that to determine the concentration of our unknown. So effectively what we do is we make these 5 solutions. We measure their conductivities and we plot them on this graph. So now we know the conductivity of these different solutions. So let's say that our unknown has a conductivity of 9,000. Well, if you look here, 9,000 is about right here, and you can see that about halfway between these 2 lines, the concentration is somewhere around 1.05% NaCl. So we can take the thing we can easily measure, conductivity. You just stick a probe down into the solution and you can measure its conductivity, and we relate it to the thing we want to know, the concentration by mass of salt in the solution, so that we can see if it's safe to inject in a person. And again, of course, this is not safe to put in a person because it's not sterilized or anything like that, but you get the general idea. We can also use the equation of the line. So 9,000, if that was the conductivity of our unknown, would be a y value. We can then solve for x, which will be somewhere around 1.05 in this case, and we can determine the concentration of the unknown. This is called a calibration curve. It's very important that your calibration curve has an r squared of 0.99 or better. If it doesn't have an r squared of 0.99 or better, please consult your TA because you may need to remake a solution or something like that. Well, needless to say, if we're going to make a calibration curve of known mass percent solutions, we're going to need a 1.2, a 1.1, a 1, a 0.9, and a 0.8% solution. So in the next section, we'll talk about how we're actually going to make those solutions. So the first thing we're going to do is we're going to make the solution and calculate the exact mass percent of the solution. To do that, we're going to need both the mass of the solution and the mass of the solute, as it says down here. So in order to do that, we have to find the mass of the solution. So we're going to start by taking a 125 milliliter Erlenmeyer flask, that's this one in the picture, and we're going to measure its mass, because we're going to need to know the mass of the empty flask so we can subtract that out once we have it filled with solution, so that we can figure out the mass of the solution. So the next thing we're going to do is we're going to make 100 grams of the 1.2% saltwater solution, and we're going to do that by difference. So basically what we're going to do is we're going to put some salt in our weighing bottle. You can kind of see it there. The lights or reflection is kind of not good, but the weighing bottle is right there. It's got some salt in it. Okay, you can see it has a mass of 16.9522 grams. We're then going to slowly, over several times, spill out the salt such that 1.2 grams are spilled out. So since this is 16.95, we want to go down to about 15.75, and being conservative at first so that we're not going to overshoot it. It's a good idea if this flask is dry. It's absolutely essential that the weighing bottle is dry. We spill out about 1.2 grams. In this case, the mass went down to 15.7507. You can see now the salt is in our flask here, and less salt is in the weighing bottle, although you can't really see it because I didn't realize there was a light reflection, but you can't really see it that well. And that gives us 1.2015 grams of salt transferred. Next, we're going to add 99 milliliters of water to this flask. We're going to, once the salt is in it, make sure that you add the water not over the balance. Then you can swirl to dissolve the solution, dissolve the salt to make the solution. So once you do that, you're going to record the mass of the whole thing. Since you have the mass of the empty flask and the mass of the solution in the flask, you can subtract, and in this case the mass of the solution is 100.4322 grams, and then we can find the mass percent by taking the mass of the salt, or the mass of the solute, all right, divided by the mass of the solution, and then we find that it's around 1.2%, which is 1.1963%. Once we have the first solution, which is going to be around 1.2%, don't worry, it's not going to be exactly 1.2%. Don't worry if it's not exactly, even if yours is 1.17 or 1.25, it doesn't really matter, okay? As long as it's around 1.2% in the ballpark, okay? Then we're going to dilute it, and this is very similar to what you've done before. So now we're going to dilute the solution to make 20 milliliters of 1.1, 1.0, 0.9, and 0.8% NaCl. And to do dilution, we're going to use the dilution equation. Concentration 1 times volume 1 equals concentration 2 times volume 2. So in order to do that, we're going to first put in our initial concentration. We're going to make all of our solutions using our 1.2% solution. Note that your 1.2% solution is not going to be exactly 1.2000%. At least it's very unlikely that it will be. V1 is the variable. How much of the 1.2% solution do I need to add to make 20 milliliters of a 1.1% solution? C2, or your the concentration you're looking for, in this case is 1.1%, but you're going to have to repeat this for 1.9 and 0.8. And the volume is 20 milliliters. I missed the unit there. That should say 20 milliliters. I think I just forgot to copy it. All right, and when you do that, you get V1 equals 18.4 milliliters. What does this mean? It means we add 18.4 milliliters of the approximately 1.2% NaCl. It's not exactly 1.2%, no big deal. And 1.6 milliliters of water. How do we get the 1.6 milliliters of water? Well, 20 is the total volume of the solution, and 18.4 are this solution. So the rest of the 20, or 20 minus 18.4, 1.6 milliliters are water. And we're going to do this into a 50 milliliter Erlenmeyer flask. Again, we use this shaped flask so that we can swirl it and mix it up. These are also convenient for measuring the conductivity using a conductivity probe. It's super important that these solutions are made inside of this flask and that the flask is labeled. Okay, so you need to make sure that the flask is labeled because all of your solutions are going to look like a clear liquid and they're all going to be in the exact same size flask. If your lab partner moves something, you're not going to know which is which. So make sure you label this, 1.1% or B if you prefer, but make sure you label it some way. I would write it as 1.1%. So now that we've talked a little bit about how to do this math, I want to show you in Excel how we can do this math. Alright, so for this section I'm going to splice together a couple of videos. So you may see some of these things move a little bit further into this video, but that's not a big deal. We don't really want you copying the exact cell addresses anyway. We want you to understand how to do this so that you can do it independently. Alright, so we have some stuff here. First thing we did was we measured the mass of the empty 125 milliliter Erlenmeyer flask before we did anything. Then we measured the mass of the salt by difference, and then we measured the mass of the Erlenmeyer flask and the solution as well. So we have all of this data in our Excel file. So the first thing we want to do is find the mass of the salt. Well, we're going to find the mass of the salt by difference. So we're going to take the weighing bottle before we poured the salt out, and then we're going to take it after, and this gives us the mass of the salt that was transferred into the flask. Then, once we have that mass of salt in the flask, what we're going to do is add 99 milliliters of water and measure the mass of the solution again. So in order to do that, we need to take the mass of the solution in the flask minus the mass of the empty flask itself. This is why it's important to measure the mass of the empty flask before we add the 1.2015 grams of salt to it. Now look, could you do the math differently and measure it after? Of course you could, but this is basically how we suggest that you do it. So then we can find the mass of the solution. So now we have the mass of the salt by difference using the weighing bottle, and the mass of the solution by taking the mass of the solution after we added the 99 milliliters of water to the salt minus the empty flask. Now we could find the concentration of NaCl in the solution, which we are going to do by taking the mass of the solute divided by the mass of the solution, and because it's a percentage, we want to multiply it by 100. Excel is like a calculator. It gives us way too many sig figs, but you'll notice this is around 1.2%, and we're not going to show you how to fix the sig figs because it gets quite complicated in some cases. So you'll note in the next step where we do the recipes of the solutions, these cells aren't in exactly the same order, okay, but this is the Excel file that you have available to you, so you're going to want to fill out all these things. Make sure you take the mass of the flask before you do the adding the salt. You measure the mass of the salt by difference, and then you add the water, not over the balance, and you take the mass of the entire solution after you swirl it to dissolve the salt. Now we need to prepare this solution with a dilution. So the first thing that we want to do is we want to find the desired percentage, how much of the approximately 1.2% we're going to use, and how much water we're going to use. Now what you need to remember is that this is not going to be exactly 1.2%. So we're going to use this value, not exactly 1.2%. So this is C1V1 equals C2V2. Specifically, it's C2 times V2, which is 20 milliliters, because we're trying to make 20 milliliters of solution, as I discussed before, divided by C1. So it's going to be C2 V2 over C1 gives me V1. How much of this that I want to use? Okay, it was 18.4 because we rounded before, and you can only really measure to 1 decimal place with a graduated cylinder. Now, how much water do you have to add? What you need to do is you need to do 20, the total volume, minus the amount of 1.2 that you're going to use, which if you recall before, it was 1.6. Now I realize I made a mistake here. In this case, I don't want this cell to drop. So when I pull this down, I want this cell to be fixed. So what I'm going to do is I'm going to put two $signs here and here. This says stick on F and stick on, in this case, 31, and then I hit enter. Okay. Now when I drag these down, it won't drag. The other way you can do this is when you click on this, if you hit F4 on a PC, it puts the $signs for you. And if you drag down, you can see that now we need to add 16.7 milliliters to make the 1% and 3.2 milliliters of this, then 15 milliliters and roughly 5 milliliters, and then 13.4 milliliters and 6.6 milliliters of water. And this will make all of the solutions that we need. Now, what I want to show you is, let's say you forget these $signs. So just click this and I don't put $signs. When you drag down, you get these divide by zero errors. Why do you get those? Because it's dragging this down to the next cell, and the next cell is divided by zero. So that's a problem. So you want to go ahead and just F4 that, and then pull down like this. I can't tell you how many times I've forgotten to do that. It's a lot. So if you forget, it's no big deal. Just go back and fix it. It only takes a second. Okay. So just reselect the cell and then hit F4, or just put the $signs in, whatever's easier for you. All right. Now you have all your recipes to make all of your solutions. So this can be very helpful. The next thing we want to do is we want to measure the conductivity of each of these solutions. So I'm going to turn it over to a live video where we show you how to measure the conductivity of the solutions, and I'm not 100% sure who's going to do that. It might be me, it might be Jesse, but we're going to show you that. Alright, so here we are in the lab, and what I have here is a large beaker of water. We're going to use this to kind of rinse our conductivity probe. This is a conductivity probe right here, and if you can see, I don't know if you can really see it, but there's like a hole where the solution gets in and it analyzes it, so it's right there, so you need to make sure your solution is above that. It also has an old headphone jack, so make sure that you have the right conductivity probe. You don't have a thermistor, which has like an Ethernet cable jack, so that's basically that. I also have my 1% solution here. So what I'm going to do first is I'm going to plug in the conductivity probe into the microlab into the port that says conductance. And then once I've plugged that in, I'm going to go ahead and start the microlab software. So what I'm going to do is minimize the live video and put the microlab software up on the screen. All right, to start the Microlab software, the first thing you want to do is make sure that your Microlab is turned on, and you can see the on light, and then you want to go ahead and click the Microlab software, and it's very important that you see this blue bar running across the screen. So let me just show you for a second what happens if you don't see that. So what you see is it'll go load into this screen, and I'm just going to go ahead and hit cancel and close this, and what I'm going to do is I'm going to turn the Microlab off. All right, and then I'm going to click it again. And if I do that, what you'll see is this. If you see this and you don't see that blue bar crawl across the screen, the software in the Microlab, the computer in the Microlab are not talking. So if I hit continue, I see the exact same screen, but I will get no measurements and no readings, and it can be confusing to try to troubleshoot in this situation because it looks the exact same. So you need to be really careful that when you load the Microlab software, I'm going to go ahead and turn it back on. When you load the Microlab software, you do have this blue bar crawling across the screen. This means that your Microlab and your computer are talking to each other, which is obviously pretty important. So the next thing that I want to do is, once this loads up properly and everything's working, I want to click on Microlab Experiment. Once I click on Microlab Experiment, I'll get to this screen. When I do that, I want to hit Add Sensor, okay? I want to choose, in this case, the conductivity sensor. And on this version of Microlab, that plugs into this headphone jack right here. And then I want to click 0 to 20,000 microsiemens per centimeter. And I want to click Use the factory calibration. Now you'll recall that this is in tap water. If we have DI water available, excellent, it'll read lower. But if we have tap water, it reads usually between 50 and 200, somewhere like that. In this case, it's reading about 130, and then it'll change based on the Microlab and based on the day of the week. So what I'm going to do is I'm going to minimize this again and try to get you kind of a screen of the Microlab and of the live view. Note that this is where we're reading the conductivity. And if it's in air, it should read 0 because it should have no conductivity. I'm just going to pull it out and just show you that. Okay, now it's not in the solution, but when I put it back in, it'll read the conductivity. So again, I'm going to just minimize this so you can see both things on the same time. All right, so the conductivity is now kind of small, but you can see it right here, and it's jumping around. I have it in my wash solution. So basically what I'm going to do is just swirl the conductivity probe in the solution and wash it off, and then just kind of try to tap as much of the water as possible off of it. You don't really need to dry it because it's only a few drops of water and 20 milliliters. It's probably okay. Then what I'm going to do is I'm going to kind of tilt my 1% solution a little bit, and I'm going to put the conductivity probe down in there so that it's nice and submerged. So I'm going to then just kind of swirl it, and you can see that the conductivity reading is increasing to somewhere around 8830, something like that. Now in the experiment it says that it's 8820, okay, but I was just trying to guesstimate it here, and they'll be a little bit different from solution to solution. So you'll notice that that measurement is jumping around quite a bit as I swirl the conductivity probe into the solution. So once you've swirled it for about 30 seconds or so, just pick a reading, okay? So this one I'm going to call 8880. Okay, so 8880 seems good, and went up to 8890. That's probably okay if you wanted to put that, but something like that. Okay, it will change a little bit, and it does tend to kind of go up as time goes on. And here it's even going into the 8900s or 8910. So once you have a reading, okay, swirl it for about 30 seconds to a minute, then pick whatever you think is a good reading. It does jump around, which I know is frustrating, but it is what it is, and there's nothing I can do about that. All right, what you want to do is swirl it back in your beaker of water, okay, and tap it off after you've swirled it in the large beaker of water, then into your next solution, and you're going to record all of your solutions. Note that for your 1.2%, the original solution that you made, you may not be able to measure that into the 125 milliliter flask. There may simply not be enough liquid in the bottom. If that's the case, just transfer it into a smaller flask and then make your measurement from there. So hopefully this gives you a good idea of how to use the Microlab to measure your conductivity. Again, I know it's a little bit of a pain in the neck because the reading jumps around, but just pick your favorite reading after it's stabilized for 30 seconds to a minute. Thanks for watching. So now that we have our conductivities measured, what we want to do is put them into Excel. So the first thing that we want to do is we want to use the exact 1.2% concentration. So if you'll remember, we didn't use exactly 1.2%. So again, we hit equals, that tells Excel to do math or to reference another cell, and we just click on that, and it tells us, it puts the exact concentration of our top solution in. Note that by the way we made all the other solutions, these are their exact concentrations. So we don't need to fix these ones. We only need to fix the first one. And you'll also notice that we measured the conductivity of an unknown at 8,300. So if we just look here at these numbers, so 1.2, 1.1, 1.9, and 0.8, 8,300 is very close to 0.9. So this is going to be the concentration of the unknown is going to be a little bit more than 0.9. But let's plot it and find out. So we highlight all of our data. We go to Insert. We click on a scatter plot like this, okay? And then if you go to this quick layout, you can find this where it nicely gives you the equation of the line, and it makes the linear regression for you. And we can just delete this so it looks a little bit nicer, and we can add our axes. So this is the mass percent on the bottom, or the concentration. I guess I should put it as the concentration by percent m over m. This is the conductivity, and that's in microsiemens. So if you want to really be careful, you can find the micro symbol. Okay, so you can insert that. Micro Siemens per centimeter, to be technically correct. Okay, and then the chart title, I'm not going to type this in for you, but it could be something like concentration of salt water versus conductivity. So that's basically that. And you'll notice that we have this equation of the line, and you'll notice that our R squared is 0.99 or better. That's really important. So what do we want to do? Well, we want to find the exact concentration of our unknown. We know it's somewhere around 0.9, but we don't know exactly what it is. So again, to get Excel to do math, we click equals. Note that conductivity, this is a Y value. So this is a Y. What's the first thing we want to do? We want to subtract this and then divide by this. Because we're subtracting first, we want to put this in parentheses because otherwise we're going to divide first because of order of operations, PEMDAS. So we just take the B70 and we divide by 335 or minus 3350.9. So first we subtract this and then we divide by that. Then we divide by our slope, which is 5441.1. So you'll recall this is the slope and this is the y-intercept. So we effectively subtract our slope in this case because we have a positive, we subtract our y-intercept in this case because we have a positive y-intercept, and then we divide by our slope, and again we have a positive slope because it is a positively sloped line. Then we hit enter, and you can see it's not quite exactly 0.99, but it's right, or excuse me, 0.9, but it's right around 0.9 for the conductivity, which is exactly what we expected because 8,300 is right around 0.9. And in this way, if we were working for a company who was making this solution, we could determine that this solution was safe to use with our patients because it has the correct osmotic pressure and it's not going to hurt anybody. Note that our solutions are not sterile. I don't think anyone's going to try to inject them, but you get the idea. These solutions are definitely not safe for that. These are just, for practice and understanding the calibration curve. So I hope you found this video helpful, and thank you for watching.